Hello learners and welcome to today's lesson. So in this lesson you're going to be discussing physical properties. Now these physical properties, they are in relation to the organic molecules, and this is what you're going to be looking at. So under the matter and material, we're going to be looking at the hydrogen bonds, the London forces, the dipole-dipole forces, chain length, branched chains, and then also looking at the physical properties that are found within the organic molecules. Now, by the end of this lesson, this is what we're hoping to have achieved. We are going to be now looking at how physical properties are affected by, number one, the intermolecular forces, the chain length, the branch chains, and the number and type of functional groups that we find in each of the organic molecules. So throughout this lesson, again, there are certain keywords that you're going to be using to better explain certain concepts in this lesson, words such as boiling point, melting point, and vapor pressure as well. So before we start the lesson, this is what I'm hoping that you know by now. You should be able now to know how to name the organic molecules using all the rules of naming, using through the IUPAC naming system. You also need to be able to draw those organic molecules that you have named. So you need to be able to draw and then name the organic molecules using the IUPAC naming system. So there are certain common errors and misconceptions that we bring into the exam room whenever we go for our exam sessions, and then these are some of them. And again, this lesson is hoping to address certain misconceptions that are having to do with this particular question or this particular concept, being the physical properties of the organic molecules. So when we are writing explanations that are related to physical properties of compounds, we are struggling to, number one, to compare the compounds that are of the same homologous series, and also to compare compounds that are from different homologous series. So whenever we're trying to explain using the physical properties, we struggle to compare properties within the same homologous series, and then we also struggle to compare properties within a different homologous series. For instance, alcohols and carboxylic acids, those are different homologous series. Again, throughout this lesson, there are certain skills that you want to engage, and there are certain skills that we want you to be able to use within an exam question whenever you're answering questions of this particular nature. However, before we start with the main topic or with the main subtopic of this lesson, let's quickly go for a short break, and I will see you just after this. Welcome back, learners. So now to start with the first subtopic, we are going to start with the main problem that has to do with this particular subtopic. So the problem here is, when we are writing the explanations that are related to the physical properties of compounds, we are struggling to follow these following steps. Number one, we are struggling to compare the surface areas of the compounds. So remember, we need to be talking about spherical substances. We need to be talking about the substances which are longer than others. So basically, that is now comparing the surface area, the space in which those substances are taking when we are drawing them specifically. Number two, we're also struggling to compare the strength of the intermolecular forces. So we don't really know how each of these intermolecular forces are different with regards to their strength and how much energy is needed for each one of them to overcome that particular intermolecular force. And then number three, we're also struggling to compare the energy that is needed to overcome the intermolecular forces, as we have said. So if we do not know the strength that each intermolecular force possesses, we aren't then going to be able to talk about the energy that is needed to overcome those intermolecular forces. So we are having these problems. Also, when we are also writing explanations that are related again still to the physical properties of compounds, we are struggling again to follow these steps. To state the type of intermolecular force in each compound, again to compare the strength of the intermolecular force, and then lastly to compare the energy that is needed to overcome the intermolecular force. So we can be given the substances And on each substance, we need to be able to tell that this particular substance possesses this intermolecular force or a combination of two or more intermolecular forces. And after having done that, we also now need to be able to talk about the energy that is needed to overcome those intermolecular forces. We know that substances with weak intermolecular forces, they require less energy to overcome them. However, the substances with a larger intermolecular force or a stronger intermolecular force, they're going to require more energy for them to be overcome. So whenever we're trying to talk about the explanations or to explain using those physical properties, we are struggling in that regard. So to start now, we are going to be looking at the hydrogen bonds and how they are related to the intermolecular forces, and also how do we then explain using what we know. So in this chapter, we are going to be now looking at specific intermolecular forces. And those ones are, number one, we have our hydrogen bonds, we have our London forces, and then we also have our dipole-dipole forces. And then these intermolecular forces, they are known as your van der Waals forces. So all three of these intermolecular forces, they are known as our van der Waals forces. However, they are different in terms of the strength. We are going to be now unpacking them and talking about them one by one to see how different they are with regards to their strength and the energy that is required to overcome those intermolecular forces. So to start now, our hydrogen bonds. So if a substance has a hydrogen bond, now that is not to say that a substance will only have hydrogen bonds. The substance will have all three van der Waals forces, but then out of those three, the hydrogen bonds are going to be the strongest. So therefore, we're going to be referring to them as having the hydrogen bonds. Not to say that they don't have the other ones. They have all three, but the strongest out of the three would be the hydrogen bonds. So if a substance has hydrogen bonds, number one, they will have a higher melting point and also a higher boiling point. So what do we mean by them having a higher melting point? So substances which have a higher melting point, those molecules that are making up that substance, they are going to be strongly attracted to each other. Number two, if they are strongly attracted to each other, that means we are going to require more energy to overcome the bonds between their respective molecules, and therefore they will relatively have a higher melting point. So a substance having hydrogen bonds or having all three intermolecular forces, but the hydrogen bonds being the strongest one, for you to overcome those substances or for you to overcome those forces that are bonding the substances together, or the molecules in this case as they stay together, we're going to require more energy. So if we require more energy, that means even the melting point is also going to increase. That means the more energy we need to overcome an intermolecular force, the higher the melting point. Now, with regards to the boiling point, still substances having a hydrogen bonds, they are going to be strongly attracted to each other. And if they are strongly attracted to each other, they will still then need more energy to overcome the bonds between the respective molecules. And once that happens, these substances will have a higher melting point. So again, the more the energy is required, the higher the boiling point and also the higher the melting point. That is only if now the substances have a hydrogen bond between the molecules that are making up that particular substance. So that's that with the hydrogen bond. So when we're now looking at the other types of intermolecular forces, we said that you're going to be looking at them one by one. So we've now looked at the hydrogen bonds. Let's look at the other ones now, being the London forces and the dipole-dipole forces. We did say that the van der Waals forces, they include the hydrogen bonds, which we've talked about, now the London forces and the dipole-dipole forces. Now these three particular intermolecular forces, how are they different? We are saying in terms of the strength, number one is going to be your hydrogen bonds. And then number two, again in terms of the strength, we're going to have your dipole. And then the weakest one out of the three would be your London forces. Like as we have said, it is not to say that a substance may not have a combination of these three, can also still have one. But if a substance is referred to as having hydrogen bonds, that means it has all three intermolecular forces, but out of the three, the strongest one being hydrogen bonds will then have a higher melting point and therefore a higher boiling point. Now, if you were to compare these two substances, the these two intermolecular forces, a substance having dipole-dipole forces and another substance having only just London forces. When you compare them, remember we said in terms of the strength, the strongest one is going to be the hydrogen bonds, followed by the dipole-dipole forces, and then lastly, we're going to have the London forces. So if you're just talking about two substances that have these two, the dipole-dipole forces and the London forces, the substance with the dipole-dipole forces will have a higher boiling point, a higher melting point, as compared to the substance that only has the London forces. Because as the strength of the intermolecular forces increases, then the energy required to overcome those intermolecular forces also increases. So the London forces are weaker than the dipole-dipole forces, which means to overcome the intermolecular forces making up the London forces, you're going to require less energy as compared to now the energy needed to overcome the substance that only has the dipole-dipole forces. So these three are all, as you have said, known as your van der Waals forces. And we are saying the London forces are the weakest intermolecular forces out of all three, and then the strongest one are going to be the hydrogen bonds, which means the dipole-dipole forces are in between. They are the second strongest amongst the three intermolecular forces. So now, learners, before we go to the next part of this lesson, let's quickly go for a short break, and I will see you just after this. Welcome back, learners. So as you have said before the ad break, we're just going to jump into our next part of the lesson. Now we are going to be looking at the chain length and how it is affected by the intermolecular forces with regards to their physical properties. So when we are now comparing substances that belong to the same homologous series, in this case, we have an example of alcohols. We are saying an increase in chain length. By that we mean the more we add carbon atoms within the chain length, we are going to increasing from 1 carbon, 2 carbons, 3, all the way to 8 carbons, or all the way to, in this case, we have up until 4. So when we are increasing the chain length, that is going to result to an increase in strength of the intermolecular forces between the molecules. So that means as the chain length increases, the strength of the intermolecular force is also going to increase. Now we are talking about the same type of intermolecular force, but it's increasing in strength within the same homologous series. That means now, if we have this this alcohol that has 1 carbon, comparing that to this alcohol that has 2 carbons. It's an alcohol because of the functional group OH on both of them. The difference between the two, it is the mass or the size of an atom, or the length it's the size of the molecule or the length of this molecule as we are seeing here. One has 1 carbon and the other one has 2 carbons. So when we are comparing these two, we know that it's an alcohol, it has the London forces, it also has the dipole-dipole forces, and also has the hydrogen bonds. Now, looking at these two, they are both alcohols, both belonging to the same type of homologous series. So therefore, as we are increasing the chain length, the strength of the intermolecular force is also going to increase. It is still the same because the prevalent one here is going to be our hydrogen bond. As we are increasing, going down from 1 carbon all the way to 4 carbons. As we are increasing in terms of the length of the chain, the strength of the hydrogen bond is also going to increase, which means this compound here, this alcohol, has stronger hydrogen bonds as compared to this one here, and this one has stronger hydrogen bonds as compared to this one, and this one has stronger hydrogen bonds as compared to the first one. And we know that as that happens, as the strength of the intermolecular force increases, more and more energy is going to be required to overcome that intermolecular force. Now, if we're looking at the boiling point then, it means this compound here, the one that has 4 carbons, will have a higher boiling point as compared to the other 3 types of alcohols because of the strength of the boiling point, or the strength of the intermolecular force that it has. So as the chain length increases, the strength of the intermolecular force is also going to increase. We are then furthermore saying the length of the carbon chain is determined by the number of carbon atoms, as we can see, 1, 2, 3, and then 4. So the length of the carbon chain is determined by the number of carbon atoms. And then it's also determined by the molecular mass or the molecular size. So as the size or the mass of the molecule is increasing, the strength of the intermolecular force also increases. So the stronger the intermolecular force between the molecules, we are saying there's going to be a higher melting point and also a higher boiling point. And if that happens then the substance must have a lower vapor pressure. So remember we said there is a relationship between the boiling point and melting point together with the vapor pressure. As the boiling point increases, the melting point also increases. However, the vapor pressure decreases. So substances with a higher boiling point and a higher melting point will have a lower vapor pressure. But substances with a higher vapor pressure will have a lower boiling point and also the lower melting point. So a substance can have both higher melting point and boiling point together with a higher vapor pressure. One has to go down and the other two will have to go up, those ones being the boiling point and the melting point. Now, if now we are looking at the branch chains, because here we're looking at the chain length, the straight chains. What happens now if the branches or if the chains are branched? If we are to look at this substance, 2-methylpropane, we know that we have a long chain that has 3 carbons because of the prop. We have a branch that has 1 carbon, that's our methyl. So in total, this compound, the 2-methylpropane, has 4 carbons. In total, it has 4 carbons. However, it is branched. So the picture that shows the name of this compound is going to be here, whereby we have our longest chain being 3 carbons, and on the second carbon, we have our branch that only has 1 carbon. So in totality, this entire compound has 1, 2, 3, 4 carbons. Now the same one can be said about this. It's a straight chain that has 4 carbons. It is still going to have the same number of hydrogens. So both of these substances have the same number of hydrogens and the same number of carbon atoms. However, the difference is in the chain length, that one it is branched and the other one is straight. So how do we then compare them here? So we are saying more branched chains are said to be more compact or more spherical. They are compact because all the carbon atoms are closer to each other. As we can see, all these carbon atoms are closer to each other as compared to if a substance only had just straight chains. The carbon atoms are going to be spaced apart the more we add carbon atoms, either going to the left or going to the right. But if a substance becomes more branched, it becomes more spherical or more compact. So the more branched the molecule is, the smaller the surface area over which intermolecular forces should act. So if a substance is more compact, that means the surface area, the space that those substances are going to take is going to be smaller because those substances are more compact. And when that happens, the intermolecular forces are going to have a smaller area that they are going to be acting on. And when that happens again, what is then now said about the energy? That is going to cause a decrease in the strength of the intermolecular force, which means less energy will be required to overcome the intermolecular forces and resulting in a decrease in melting point and also a decrease in a boiling point. So the more compact the substance is, less energy is required to overcome those intermolecular forces. But the more longer the chain becomes, or the more straighter the substance becomes, or the more straighter the chain becomes, more and more energy is going to be required. If we require more energy, that means we are going to increase the melting point and also increase the boiling point. And once we are increasing these two, the melting point and the boiling point, we are going to be decreasing the vapor pressure. So those two things are going to be inversely proportional. So when looking at these two substances, the 2-methylpropane will have a lower melting point and also a lower boiling point than the butane. Why do we say that? Because this one, it is more spherical, which means there's less energy required to overcome all the substance or all the intermolecular forces that we are finding here. We also need to remember that this is an alkane, and the alkane has the London forces. Alkane has London forces. However, we did say that London forces are the weakest intermolecular forces out of the three that we have. London forces, dipole-dipole, and hydrogen bonds. But if we are just comparing the alkanes, we are saying they all have the London forces, but as we increase the number of carbons, the strength of those London forces is going to increase. So that means a methane will have only one carbon atom, whereas an ethane will have two carbon atoms, propane will have three carbon atoms. So the more we add carbon atoms, the strength of the London force is going to increase, which means if you're comparing propane and the methane, propane is going to require more energy to overcome the London force as compared to the methane that only has one carbon, which will require less energy to overcome the London force. Even though it's the same type of force, which is weak. However, it becomes stronger and stronger within the same homologous series. But then it now becomes different if we are comparing two different homologous series. Within the homologous series, the strength is going to increase. But now when comparing two different homologous series, we now need to compare the type of intermolecular force that each one has, which is what we're going to be doing now. So if we are comparing now two different homologous series, we need to be able to know how to explain that. We are saying the relationship between physical properties and the number and type of functional group plays a very, very much important role in this regard. How does it do that? Let's look at now the carboxylic acids and the alcohols. We are saying the carboxylic acids have a relatively higher boiling point than alcohols of comparable masses. Now, when we are comparing substances, we need to make sure that the number of carbon atoms on each, they are the same. We can't compare a propanoic acid with a methanol, because now propanoic acid will have 3 carbons, whereas a methanol will have 1 carbon. We need to compare the same with the same number of carbon atoms within two different homologous series. If we are comparing a carboxylic acid that has three carbons, we need to do the same thing with an alcohol. It must have 3 carbons. So it must be a propanoic acid and a propanol. So that can be a fair comparison. So carboxylic acids have a relatively higher boiling point than alcohols of comparable molecular mass. Carboxylic acids, as we have said earlier on, that they have 2 sites for hydrogen bonding, while alcohols, they will only have 1 site for hydrogen bonding, which therefore means the intermolecular forces between the carboxylic acids, they are going to be stronger than those that we find in the alcohol molecule. Even though they have the same type of intermolecular forces, they have all 3. London forces, dipole-dipole forces, and the hydrogen bonds. However, the carboxylic acids are going to be stronger than the alcohols because of those 2 sites of hydrogen bonds as compared to the one that an alcohol will have. So these pictures here, they are showing the 2 sites that if we have an alcohol bonding with another alcohol, there's only going to be one hydrogen bond that we are seeing there between the OH, between the O and the H. But when we are looking at the carboxylic acid, the COOH, we are going to have 2 hydrogen bonds there. And obviously we know that 2 is bigger than 1, and therefore the carboxylic acids are going to be stronger than the alcohols. So we are going to start with the multiple choice, and the first question that is given to us is as follows. Which one of the following compounds has dipole-dipole forces between its molecule, or between its molecules? So specifically, we are looking for a substance that has dipole-dipole forces. Now remember, these ones, they are part of the van der Waals forces, and then there are 3 in total. We have the hydrogen bonds, we also have the dipole-dipole forces, and then lastly we have the London forces. Now in terms of the strength, we know going from hydrogen bonds to London forces, the strength is decreasing. But going from London forces going to hydrogen bonds, the strength is increasing. So these ones, this is the strongest one, followed by the dipole-dipole forces, and then the London forces are going to be the weakest intermolecular forces out of the 3 that we have there. So now we are looking at a molecule that has the dipole-dipole forces. We need to know that. We have ethanol, and ethanol, it is an aldehyde. It's an aldehyde because of the suffix al. And then we have ethane, and that is an alkane because of the suffix ane. And the third one, it is going to be our alkene because of the suffix ene. And then the last one is our alkyne, the suffix yne. However, B, C, and D, alkane, alkene, and alkynes, those ones are hydrocarbons. And we know that the hydrocarbons, they only consist of the London forces. Whereas the aldehyde has both the London forces, and the dipole-dipole forces. But out of the two, as we have said, the dipole-dipole forces are stronger than the London forces. So the molecule that has the dipole-dipole force in this case is going to be A, and that is our correct answer there, A, ethanol. The next question says, which one of the following isomers, remember, isomers, same molecular formula, but we can have three different types of them. They could be the different chain length, different functional group, and also different position of the functional group. So we have chain isomers, we have positional isomers, we also have the functional isomers. So here we are asked about the ones that has the lowest boiling point. They are isomers, and one of them has the lowest boiling point. So if they are isomers, that means all of these compounds, A, B, C, and D, they all have the same molecular formula. So they have the same number of carbons and the same number of hydrogens. So the molecular formula of these compounds, let's count. We have 1, 2, 3, 4, 5, 6. It's going to be C6. It's 5, 7, 9, 11, and 14. So it's C6H14. So all of these compounds, they have the molecular formula C6H14. But looking at how they are different, we need to now check how are they different. So this one is a straight chain because there are no branches that are connected or that are shown in this compound. Whereas compound B, the bracket that we are seeing here, it shows the branch. It shows that on carbon number 3, or rather in this case on carbon number 2, because you're going to start counting from the right hand side. On carbon number 2, we have 2 branches, and those branches, they are each containing 1 carbon atom. So we are seeing that is a branch because that's in a bracket, and this is the number of the branches. So if you were to draw this compound, 1, 2, 3, 4, and then on this carbon here, there's going to be a CH3. On this carbon, there's going to be a CH3, hence the 2 there. And then on each one, we are going to have, on this carbon here, we're going to have 1, 2, 3, hence the 3. And then on this carbon, we have the 2 branches of CH3. That's why we don't have an H next to the carbon. Whereas on this carbon, there's 2 hydrogens, which is there and there. And then on this carbon, we have 3 hydrogens, 1, 2, and 3. So that's what we have for that. Now, this one here only has 1 branch. Whatever that is inside the bracket is a branch, and if there's a number, a subscript there, that subscript would show how many branches of the same type are found in that carbon. So that means this one will only have 1 branch. We have 1, 2, 3, 4, 5 carbons, and then we have another one that is going to be on carbon number 2. So if we were to draw this again, it would be 1, 2, 3, 4, 5. On carbon number 2, we have a CH3. Then we have an H because it's CH and then the CH3. Then we have the 3 H's on the first carbon, which is that one there. Then there we have 2 hydrogens, 1, 2. Then we also have 2 hydrogens again, 1, 2. Then we have 3 hydrogens, 1, 2, and 3. Now looking at this, so we have 1, 2, 3, 4, 5 carbons, and then the 6th one is the branch. Now looking at this chain, we have 1, 2, 3, 4, 5, but then we notice that our carbon atom, it is on carbon number 3. It's on carbon number 3 again, starting it's on carbon number 3, starting from the right-hand side. So it's going to be similar to this one. However, we know that for a substance to have a lowest boiling point, it means that it needs to have weak intermolecular forces. And seeing that we are comparing alkanes here, we can talk about the chain length here. In this case, the more spherical or the more compact a substance becomes, the lower the boiling point, because there's going to be less energy required to overcome those intermolecular forces. So the one that is more compact, when you're comparing all of them, would be the one that is more branched. So the one that has 2 branches in it is more branched, and therefore it is more compact, which means less energy is required to overcome those intermolecular force. In this case, because we are having just hydrocarbons, to overcome these intermolecular forces, we're going to require less energy. Less energy translates to lower boiling point and also lower melting point. So the one that has the lowest boiling point amongst all 4 of these substances will be the one that is more branched, which is B. Moving right along, we are now told here that learners are using compounds A to C that are shown here. They are trying to investigate a factor which influences the boiling point. A factor must influence the boiling point of organic compounds. So we have substance A, B, and C. Now again, on this substance, we are looking at the same type of homologous series, because all 3 of these compounds, they are hydrocarbons, and this one has 4 carbons. And how many hydrogens? We count, it has 10 hydrogens. So it's C4H10. And the second one, 1, 2, 3, 4, 5, it is going to be C5. When you count the number of hydrogens, it is going to be 12. And then this one, 1, 2, 3, 4, 5, 6, it's going to be C6. And then when you count the number of hydrogens, it's going to be 14. So that means we are seeing that the difference between each one of these, it's just the CH2. So they are different by CH2. So what is it that these learners are trying to investigate? They're trying to investigate which factor is influencing the boiling point. Now, looking at these 3 substances, we know the chain length is increasing. Because they are within the same homologous series, we are looking at the chain length. It is increasing. All of them are straight chains because none of them is branched. So as the chain length increases within the same homologous series, there's going to be an increase in the strength of the intermolecular force that we find. Now, seeing that here, we are looking at the alkanes. That means all of these substances, they have just the London forces. They have the London forces. So the strength of the London force is going to increase as you're going from one substance to the other within the same homologous series. So in this case, from butane, pentane, and hexane, as you're going down that route, the strength of the intermolecular force is going to increase. So question is, which one of the compounds A, B, or C has the highest boiling point? The highest boiling point, it is going to be influenced or is going to be given by an increase in the strength of the intermolecular force. And the increase in the strength of the intermolecular force is going to be determined, in this case, by the increase in the chain length. So the one that has the longest chain length will be the one that will have a stronger intermolecular force, which means that is going to translate to a higher boiling point. So in this case, compound C is going to be the one that has the highest boiling point. And we know the reason it is because of the chain length that is increasing within the same compound, or rather within the same homologous series. Then we are also now still given the same 3 compounds, and then now they want us to be able to write down the independent variable and the dependent variable. So knowing variables is very important, especially in chemistry and physics as well. We need to know what happens on each variable, what makes each variable to be different from the other variables. We know that we have 3 in total. We have the controlled variable, we have the independent variable, and then we have the dependent variable. We need to know that how each of them are different from each other. We should now, for you to be able to remember, just think of, so you're saying, can I dance to soul candy music? That is to say, the controlled variable is kept the same, whereas an independent variable, it is changed, and then the dependent variable, it is measured. We should never make a mistake of rewriting our apparatus or chemicals as variables. So in this case now, we are told which one is independent. We know that independent variable, it is changed. So what are they changing here? We are not going to be saying that they are changing the substance or they are changing the alkane. What basically is being changed here is the chain length from substance A, substance B, and substance C. What is different in each one, it is just the chain length. So the independent variable, as we have said, it is changed, so therefore it is the chain length. But what is kept the same there here is going to be the homologous. So the same homologous series is kept the same. So which means what is kept the same, it is going to be the intermolecular force, because we are looking at the same intermolecular force being the London force. So what is changed is going to be the chain length, but what is dependent? Remember, dependent, it is what is measured. So this is going to be given by the statement given to you. We are reading here that learners are using compound A to C shown in the table to investigate a factor which influences the boiling point. So for them to see that the boiling point is going to be influenced, they need to measure the boiling point of each organic molecule. So therefore the boiling point is going to be our dependent variable. So this is our boiling point. Right. So before now we go to the next part of these questions, we are just going to quickly go for a short break, and I will see you just after this. Welcome back, learners. So again, we are continuing with the same topics, or with the same questions rather, that have to do with the physical properties of organic molecules. So now the question is, we need to write down the name of the type of the van der Waals force that occurs between the molecules of compound B. So compound B, we need to write down the type of the van der Waals force that occurs here. Now this is an alkane. How do we know that it's an alkane? Because of the chain length and also because of the way in which the carbons are bonded to the hydrogens. We do not have any double bond or any triple bond here, and it is a bond between carbon and hydrogen. So therefore it's an alkane known as a hydrocarbon. And now, because it's an alkane, all the alkanes are going to have the London forces. Question 4 now says, how will the vapor pressure of 2-methyl pentane compare to that of compound C? Write down only higher than, lower than, or equal to. So we now need to compare 2-methyl pentane with compound C. Compound C, from the looks of it, we're seeing that it has 6 carbons, and then it has 14 hydrogens. If you had to count the hydrogens, that is 5, that's 9, and then that is going to be 14. So it's going to be C6H14. And then looking now at your 2-methyl pentane, that is now going to be, pent means 5 carbons, and then the methyl means it's another carbon, but that carbon, it is branched. So however, in total, the compound will still have 6 carbons and 14 hydrogens. So those two substances, they are actually isomers. They are actually, to be specific, they are structural isomers, because this one is branched and this one is a straight chain. They still belong to the alkanes, but then one is branched and the other one isn't. Or we can say one is more compact or more spherical because it is branched. So how do we then compare now the vapor pressure? We do know that if a substance has a higher melting point and a higher boiling point, it needs to have a lower vapor pressure. But if a substance has a higher vapor pressure, it needs to have a lower boiling point. So comparing these two, this is a straight chain, that's a branched atom. A branched atom requires less energy to overcome the intermolecular forces as compared to a straight chain. That means the 2-methyl pentane is going to have a lower boiling point and also a lower melting point, which means it is going to have a higher vapor pressure as compared to compound C. So then the answer to this question is going to be higher than. So how will the vapor pressure of 2-methylpentane compare to that of compound C? It is going to be higher than. Reason is there's less energy needed to overcome all the intermolecular forces present in this molecule. So now we need less energy here. However, on compound C, we need more energy. The moment we need more energy, it means that substance will have a higher boiling point and a higher melting point, and therefore the vapor pressure is going to be lower. And the opposite is true. The moment we need less energy to overcome the intermolecular forces, that substance will have a higher vapor pressure and therefore lower boiling point and lower melting point. So these learners now are comparing the boiling points of compound D and E as shown in the table alongside. Question is, how does the boiling point of compound D compare to that of compound E? We only need to write down higher than, lower than, or equal to, and thereafter fully explain our answer. So the two compounds that we have, we are seeing that at the end of this chain there's an OH, and at the end of compound E there's COOH. We know that OH, that's your hydroxyl group, and then your compound E, that's your carboxyl group. So therefore, this is an alcohol, so compound D is an alcohol, and compound E is your carboxylic acid. Now remember that carboxylic acids, they have two sides. Of hydrogen bonding, whereas the alcohols only have one side. And because of that, when you're comparing now in terms of the boiling point, because of that, the carboxylic acids are going to be stronger than the alcohols, and therefore that means more energy is going to be required to overcome the strength of the intermolecular force found within the carboxylic acid substance. So how do we then respond to this question? Remember, we need to make sure that three things are met, or three things are talked about. Number one, we need to talk about the type of intermolecular force. Number two, we need to talk about the strength of the intermolecular force. And then lastly, the energy. So we need to make sure that in our response, we talk about the type of intermolecular force that we find on each of these two compounds, compound D and compound E. And then number two, we talk about the strength. Which one is stronger than the other? Now we have a clue now between the two that the carboxylic acids have two sides of hydrogen bonds, whereas the alcohols have one side of hydrogen bond. So that now gives you a clue on which one is stronger than the other. And because of that, as a result, which one is going to require more energy to overcome those intermolecular forces? So now let's respond to the question. So in response to the question again, we need to go back to it, alcohols versus the carboxylic acids. When we start, we are saying the question says, how does the boiling point of compound D compare to that of compound E? So compound D is going to have a lower boiling point as compared to compound E. So we start by answering the question. Remember they said, write down only higher than, lower than, or equal to. Then after we explain our answer. So it is lower than, D is lower than E, because both compounds D and E have hydrogen bonding between molecules. That's now the type of intermolecular force. And then bullet number two, compound D has one side for hydrogen bonding, whilst compound E has two sides for hydrogen bonding, or that means it's going to form dimers. So because of that, because of the two sides and one side, we can then conclude to say that compound E is stronger than compound D. So the strength of the intermolecular force on compound E will be stronger than the strength of the intermolecular force found in compound D. And because of that, more energy is going to be needed to overcome the intermolecular force in compound E. Or we can also talk about the other one to say less energy is going to be needed to overcome the intermolecular force in compound D. So now if you are looking at compound E will require more energy to overcome the intermolecular forces within itself. And then compound D will require less energy to overcome those intermolecular forces found within that alcohol. So that's how we now are going to be structuring our response. Type, and then this bullet talks about the strength. And then the last bullet talks about the required energy. So energy that is needed either in compound E or compound D. Now remember, for that one, you need to be specific. If whether you're talking about compound E or compound D, you need to be specific. So before we move on now, learners, let's quickly go for a short break, and I will see you just after this. Welcome back, learners. So in this lesson, remember, this is what we looked at under matter and material. We looked at the three types of the van der Waals forces. We looked at the chain length. We were comparing now substances with regards to the chain length. We looked at the substances and compared them with regards to their branched and also how long they are in terms of the chain. And then we looked at the physical properties, how to compare substances with regards to the physical properties and the intermolecular forces that you find in each of these substances. Now, again, in this lesson, there were certain keywords that we used to better explain certain concepts, words such as boiling point, melting point, and vapor pressure. And we tried to address the misconceptions that you normally bring into the exam session or whenever we're writing our test and exam question papers. So we are saying that when writing explanations that are related to the physical properties of compounds, we are struggling to, number one, compare compounds from the same homologous series, and we are also struggling to compare compounds that are from different homologous series. So we are struggling to compare from the same and also from different homologous series. And then again in this lesson, there were certain skills and certain exam writing competencies that we tried to engage, and I hope that when you do this on your own, you are going to be able to engage some, if not all, of these exam writing competencies, and especially when you are writing your exam question papers, you need to engage most of these exam writing competencies when you do that. So if you want to try these and similar questions, these are the papers that I'm suggesting that you go through, see if whether you can be able to do them on your own, go through the lesson, see if whether there are certain skills that you can pick up, and also try to apply those skills into your answering of the exam question papers. You can do all of them or you can do some of them, but the most important thing is you need to make sure that you are doing something. Up until I see you next time. Goodbye.